Hi everybody. This is the last in our series of videos about statistical mechanics. We're going to build on some of the ideas that we developed in the previous videos about individual atoms and diatomic molecules to think about the properties and specifically the heat capacity of polyatomic ideal gases. This is the summary slide from the end of the previous video that shows the partition functions and properties of diatomic ideal gases broken down by the various types of motion: translational, rotational, vibrational, and electronic. You can see in the last column, highlighted in blue, that each type of motion makes a contribution to the molar constant volume heat capacity. Translational motion contributes 3/2 R. Rotational motion contributes R, assuming the temperature is more than a few Kelvin. And vibrational motion makes a contribution that approaches 0 at very low temperatures and approaches R at very high temperatures. As we'll see, all of this information about diatomic molecules is part of a larger picture that applies to all molecules that we'll develop in this video. In order for us to generalize these ideas, we first have to talk about the modes of motion of a molecule. If a molecule has n atoms, then it has a total of 3n modes of motion, basically 3n coordinates along which that molecule can move. The reason for that is pretty simple. There are n atoms, and each of those n atoms can move in 3 dimensions, the x, y, and z dimensions. So that's 3n coordinates. We're not really concerned about these individual movements of the atoms. We're actually concerned about the collective movements of the molecule as a whole. But that total of 3n coordinates isn't going to change. The 3n modes of motion that we're concerned about break down in terms of translation, rotation, and vibration. In all cases, whether we're talking about individual atoms or diatomic molecules or polyatomic molecules, there are always going to be 3 translational modes: collective movements of the entire molecule in the x, y, and z dimensions. For each of these types of motion, I'm going to use water as an example. And in these pictures, the water molecule is moving in all 3 dimensions: left to right, bottom to top, and in and out of the slide. The number of rotational modes depends on what type of atom or molecule we're looking at. In the case of water, which is a nonlinear molecule, there are 3 rotational modes, basically rotation around the x, y, and z axes. If we're looking at individual atoms, there are no rotational modes because rotation doesn't change the position of anything. And if we're looking at a linear molecule, there are only 2 rotational modes because rotation around the bond axis doesn't change the position of anything. And whatever number of modes are left are going to be vibrational modes. In the case of water, which has 3 atoms, there are 3n or 9 total modes. Since 3 of them were translations and 3 of them were rotations, the remaining 3 must be vibrations. These pictures show the 3 vibrational modes of water. One is a symmetric stretch, one is a bend, and one is an asymmetric stretch. In another course, you might learn a little bit more about these different types of vibrational modes. But here, we're just going to focus on how many vibrational modes there are. Each of these types of motion makes a characteristic contribution to the heat capacity of a molecule. For the 3 translational modes, each one contributes R/2 to the molar constant volume heat capacity. This is consistent with what we've seen before. We've already seen for individual atoms and for diatomic molecules that the translational contribution to the molar constant volume heat capacity is 3R/2. That's R/2 for each of the 3 translational modes. And that's no different for polyatomic molecules. Any atom or molecule will have a translational component of the heat capacity of 3R/2. For the rotational modes, each one of those also contributes about R/2 to the molar constant volume heat capacity. I say approximately R/2 because again we're making the assumption that the temperature isn't too low to excite rotational modes. Again, this result is consistent with what we've already seen. We saw for diatomic molecules, which are linear and have 2 rotational modes, that the rotational contribution to the heat capacity is R. That's 2 modes, each of which makes a contribution of R/2 for a total of R. If we're looking at a nonlinear molecule, there are going to be 3 rotational modes and a total rotational contribution to the heat capacity of 3R/2. And for the remaining modes of motion, which are vibrational modes, each one contributes up to R to the molar constant volume heat capacity, Again, it's this situation where at low temperatures, the contribution is 0, and at very high temperatures, high enough to excite a lot of vibrational states, the contribution approaches R. This is also consistent with what we've seen before. A diatomic molecule has 6 total modes of motion, 3 of which are translational, 2 of which are rotational, and therefore 1 of which is vibrational, and that one mode contributes nothing to the vibrational heat capacity at low temperatures and contributes R to the vibrational heat capacity at high temperatures. This is kind of a lot of information to process, so I'd like to go through an example where we find the approximate molar constant volume heat capacity of a polyatomic molecule. We're going to use the example of ammonia, NH3, and the question that I have is that if the temperature is high enough to access the vibrational excited states, but not so high that it accesses the electronic excited states, then what is the approximate molar constant volume heat capacity? I'll give you a few seconds to think about it. So here's the question, and to think about the different types of motion, we're going to make a table. If we first consider the translational modes, we know that any atom or molecule has 3 translational modes. Each contributes R over 2 to the heat capacity, so the total translational contribution is 3R over 2. Because this is a nonlinear molecule, there are 3 rotational modes. Each contributes R over 2 to the heat capacity, so the total rotational contribution is 3R over 2. And in this case, there are 6 vibrational modes. Because ammonia has 4 atoms, that's going to be 12 total modes, so if 3 are translational and 3 are rotational, that leaves 6 that are vibrational. We're told in the question that the temperature is high enough to access vibrational excited states, meaning that each of those vibrational modes is going to contribute approximately R to the molar constant volume heat capacity for a total vibrational contribution of 6R. And to find the total heat capacity, we just have to add those together. These 3 types of motion are basically just different buckets into which the molecule can take in energy, so we just have to add the 3 contributions together to get 9R. If the question had told us that the temperature were too low to access vibrational modes, then we would have just taken away that vibrational contribution and said that the heat capacity was approximately 3R. So this is kind of a rough way of solving this problem, assuming that the temperature is either very low or very high. We're going to go through one more example in this video in which we try to think a little bit harder about what happens at intermediate temperatures. We're going to use spectroscopic data to estimate the molar constant volume heat capacity of a Buckyball, a C60 molecule, at a temperature of 1000 Kelvin. So in this case, we're not assuming that the temperature is very low or very high. We're actually told the temperature, and we need to interpret what that means. Before looking at the spectroscopic data, I want to ask the question of how many vibrational modes there are in a C60 molecule. I'll give you a few seconds to think about that. C60 has 60 atoms, which means it has 3 times 60 or 180 total modes of motion. 3 of those modes are translational. Because the molecule is nonlinear, 3 of those modes are rotational, which leaves 174 vibrational modes. It's a big molecule, so there are a lot of them. This table shows the vibrational frequencies, in spectroscopic units of reciprocal centimeters, for those 174 vibrational modes. When you take the degeneracy of each mode into account, which is shown in the column on the left, you can take my word for the fact that there are 174 vibrational modes in this table. And those modes have a variety of different vibrational frequencies. Where you see lower vibrational frequencies, that basically corresponds to vibrational modes that you can think of as looser springs, that have quantized vibrational energy levels that are closer together. And the higher vibrational frequencies are stiffer springs that have energy levels that are spaced farther apart. At a given temperature, in this case 1000 Kelvin, we need to think about which of those vibrational modes have energy levels that are spaced too far apart to be excited, and which of those vibrational modes have levels that are close enough together that they can be kind of switched on at 1000 Kelvin. So what we're going to do is think about how many of these vibrational modes have a vibrational temperature that's at or below 1000 Kelvin. Those are the modes that can be excited at 1000 Kelvin and will contribute approximately R to the heat capacity. So once we figure out how many of those modes there are, we can estimate the molar constant volume heat capacity at 1000 Kelvin. So what we're going to do next is to find the vibrational frequency in units of reciprocal centimeters that corresponds to a vibrational temperature of 1000 Kelvin. This is kind of going to be the cutoff point of which modes are excited and which modes are not excited at 1000 Kelvin. The definition of the vibrational temperature, as you may remember, is h nu over kb. We can rearrange that to say that the frequency nu is equal to kb times the vibrational temperature over h. And if we plug in the values of kb, h, and the vibrational temperature that we're interested in, we can find the value of nu, the vibrational frequency, 2.084 times 10 to the 13th reciprocal seconds. Now we just need to convert this frequency to units of reciprocal wavelength, and we can use the relationship between wavelength, frequency, and the speed of light. 1 over wavelength equals frequency over the speed of light. We can plug in the value of frequency that we just found and the speed of light to find a reciprocal wavelength first in reciprocal meters, and then we can convert that to reciprocal centimeters. I suggest that you take your time and look carefully at each of those steps. Most of them are basically just unit conversions. So what we found here is that a vibrational temperature of 1000 Kelvin corresponds to a wave number of 695 reciprocal centimeters. That means that if the temperature is 1000 Kelvin, then any vibrational frequencies that are below 695 reciprocal centimeters have energy levels that are spaced close enough together that they will be excited and they will contribute to the molar constant volume heat capacity of the molecule. But any vibrational frequencies that are above 695 reciprocal centimeters are spaced too far apart and won't contribute to the heat capacity. It's still a big approximation to assume that the vibrational modes are either switched on or switched off. But this is already much better than we were doing before, where we assumed that the temperature was so low that no vibrational modes could be excited, or so high that all the vibrational modes could be excited. So now we can go back to the spectroscopic data, and I've highlighted in red all the vibrational modes whose frequencies are lower than 695 reciprocal centimeters. When we take into account that many of those modes are degenerate, we can say that there are 53 vibrational modes with frequencies lower than 695 reciprocal centimeters, meaning 53 vibrational modes that we can assume each contribute R to the molar constant volume heat capacity. When you add that to the translational contribution of 3/2 R and the rotational contribution of 3/2 R, we estimate that at 1000 Kelvin, the molar constant volume heat capacity of a buckyball is about 56 R. Again, we made some significant approximations here, but at least we attempted to take into account the fact that different vibrational modes have different energy spacings. Finally, I'd just like to sum up a few key points from this video. We've seen that the molar constant volume heat capacity of a molecule is a sum over translational, rotational, and vibrational modes. And basically, each of these types of motion are just different ways for a molecule to take in energy. Of those three contributions to the heat capacity, we're pretty much always in a situation where the temperature is high enough for translation and rotation to make their full contributions to the heat capacity. But the vibrational contribution to the heat capacity depends on temperature, so we need to put some thought into the spacing of the vibrational energy levels. That's all for now. The next video will be a bit of a palate cleanser between our coverage of statistical mechanics and our coverage of thermodynamics, where we review some macroscopic properties of ideal gases.